Okay. Director of PRL, Professor Anil Bharadwaj, Professor Pallam Raju, Dean PRL, Professor R.G. Deshpande, Registrar PRL, our honorable guest today, Professor Rama Govindarajan, my PRL colleagues in Ahmedabad, USO, and Mount Abu, and the audience who are attending this program online. Very good morning to everyone. I wish a happy International Women's Day to all in advance, and welcome to the 6th day of our activities to celebrate womanhood during the week of the International Women's Day. Today is a very special event in this series, the third Bibha Chowdhuri Memorial Lecture. It started 2 years ago in the honor of former PRL woman scientist, Dr. Bibha Chowdhuri. First lecture in this series was delivered by Dr. Archana Sharma from San, Switzerland. Second lecture was given by Gagandeep Kang from Christian Medical College, Vellore. And this is actually the first time this event is offline. And Dr. Rama Govindarajan, who is a professor and Dean Academic from International Center for Theoretical Sciences, Tata Institute of Fundamental Research, Bangalore, is with us today. I welcome you, ma'am, on the behalf of PRL and PRL Women's Cell. It is a great pleasure to have you here today. Now, I would like to request our Honorable Director, Professor Anil Bharadwaj, to please come on the stage for his opening address.
Oh, I am seeing myself here. I see. Oh, this is the camera. The new setup. Namaskar, Suprabhat, Yencho, Adabars, Kambagadi, Vanakam, Ram, Radhe Radhe, Jai Shri Krishna. A hearty welcome to all of you for the third Bibha Chowdhuri Memorial Lecture. This is the third in the series of lectures which we have started 2 years back to celebrate one of the very distinguished physicists or scientists of the country, Dr. Bibha Chowdhuri, who worked here in PRL for almost a decade. She joined PRL in the year 1966, to be precise, and worked for about a decade here before moving on to Calcutta. She is one among the unsung heroes of the country. And in last couple of years, there has been a lot of, research on the work which she has conducted in India, more particularly related to cosmic rays and things like that. And in view of this, there has been a book which has been written on her, which was released 2 years back. And also, there is a special issue of Indian Physics Association called Physics Today, which also came about 2 years back, of which you were one of the editors, right? And she has worked on some very novel areas, or I should say novel physics, which was quite not known. And after her research and PhD in UK at Manchester, she was, I think, working in TFR for some time. And then she was actually invited by Dr. Sarabhai to come and join PRL. So that was her, what I should say, her area of research, which was quite booming at that time in terms of the cosmic rays research. And because of the interest of Dr. Sarabhai, she was called here to join as a fellow and then as a faculty, and to start some of the new areas at places where cosmic ray research is not being carried out, which also include setting up certain observatories in places like Mount Abu, which is one of the hill stations. And PRL already had a presence that time because PRL started the ozone measurement in 1951 from Mount Abu. So today we are thankful to Dr. Rama Govindarajan Professor of and Dean of Academics at ICTS PFR in Bangalore. And she'll be talking to us on dynamics of small particles in flow, giving us the third Bibha Chowdhuri Memorial Lecture. So I welcome her to PRL, and probably after a decade or 2 decades. PRL has changed a lot in the last 2 decades, so you may be seeing some changes here also. And I also welcome all the colleagues of PRL as well as those who have joined us live on YouTube channel of PRL as well as on the WebEx. So with this, once again, welcome to PRL and to the third Bibha Chowdhuri Memorial. Thank you.
Thank you very much, sir. And to introduce Dr. Bibha Chowdhuri, who was the first Indian woman in the field of high energy particle physics, I would like to invite on stage one of the finest women scientists in high energy physics, Professor Shivati Goswami. Thank you, Yogita, for your kind introduction. And it's a privilege for me to stand on this podium and introduce Dr. Bibha Chowdhuri. And Dr. Bibha Chowdhuri, as Yogita mentioned, is the first high energy women particle physicist in India. And at that time, actually, she worked on experimental physics. So I think that's also very remarkable. She did her PhD in Rajabazar Science College in Calcutta. You know, I am also an alma mater from Rajabazar Science College. And then during 1938 to 42, she worked with Professor D.M. Bose in Bose Institute, which is next to the Science College, Rajabazar Science College. And she worked on cosmic ray particles. So they exposed some emulsion plates, and you know, the detection of high energy particles through photographic plates was at that time very new. And another pioneering women scientist, Marietta Blau, actually initiated this process, which her student, Hartha Wambaker, and Bose and Chowdhury used this photographic plate technique to detect cosmic ray particles. They published 4 papers in Nature, and it is very widely debated that whether they were the first to discover the pi meson or not. However, I have read their papers, and there are also discussions about it. Their paper, they very clearly could not mention that, you know, these are pi mesons, because actually there was a limitation of the experiment. They were using this photographic emulsion plates, and the photographic emulsion was on one side. And if they had the photographic emulsion on both sides, then they would have had much more resolution, and probably they could have said something more definite. So, which is definitely a missed opportunity for India. And actually, at that time, there was not enough funding to procure those kind of photographic plates. So that research was stopped there. And then Bibha Chowdhuri, you know, it's so remarkable that she went to another place in Manchester to work with PMS Blackett, who also got Nobel Prize later. So that was, I think, a remarkable spirit, that when she realized that the work could not be done very well in India, she chose to go to the best place. So she had the talent and the initiative both to go to that place and work there. Once she did PhD, she joined TIFR. After spending few years in TIFR, she went to some other very, prominent places like École Polytechnique in Paris, Michigan, in University of Michigan in US. She worked on, for her PhD, something called extensive air shower arrays. And she worked with people who were proponents of extensive air shower arrays in these places. So it's not very surprising that Dr. Sarabhai wanted to recruit her here, because PRL was also a center for cosmic ray research at that time. So Bibha Chowdhuri fitted in very well. She brought the subject of extensive air shower array in PRL. She joined here as a fellow in 1966. Before that, she was a CSIR SRF and a pool officer, and she worked in Kodaikanal, and later she worked on the
polar gold field, and it was an experiment conducted directly with TIFR. And she had a PhD student, Y.C. Saxena, who later joined Institute of Plasma Research. Now, after she left PRL around 1976, and they published few papers on this. And what Professor Saxena told me was that at that time, she wanted to publish papers only in Indian journals. So Professor Saxena told that these were very good papers, but she wanted to publish them in Pramana. So she left TPRL, she went to Shah Institute, she went to Calcutta, and then she worked with the researchers in Shah Institute, Cultivation of Science, Calcutta University. Now, I am from Calcutta. I had association with all these places, including TIFR and PRL, and until very recently, I have not heard of her. So that's the thing, that history somehow forgot her, and the book which Professor Bharadwaj mentioned by Rajinder Singh and Shuprakash Roy, Jewel Unearthed, brought her into limelight again. And so we thought that in PRL that we should organize something to honor her, in memory of her, also to celebrate women scientists. And that's how we started this lecture 3 years back. And I'm very happy that today is the first in-person event of this. And I really pay my homage to Dr. Bibha Chowdhuri, and I am very privileged that I have the opportunity to do that. Thank you.
Thank you very much, ma'am. And I request Professor Pallam Raju, Dean PRL, to come on a stage to introduce today's speaker, Dr. Rama Govindarajan, and also to formally conduct this session.
Good morning, friends. We have a distinguished scientist as a speaker for the third Dr. Bibha Chowdhury Memorial Lecture. And she is Dr. Rama Govindarajan, who is a professor and the Dean of the International Center for Theoretical Sciences, ICTS, at TIFR Bangalore. Professor Rama Govindarajan's research area is fluid dynamics, especially specializing in instabilities, particulate flows and the flows with the phase changes. And she had her PhD in aerospace engineering from the Indian Institute of Science. And later on, she moved on to Caltech for her postdoctoral stint. And she returned back to India, and she was on the faculty at the Jawaharlal Nehru Center for Advanced Scientific Research, and later at TIFR Hyderabad, before moving to ICTS. She is a fellow of all the three Indian Science Academies and of the American Physical Society. She's also won the prestigious Dr. Shanti Swarup Bhatnagar Prize for Engineering. We thank her for agreeing to come to PRL to deliver this lecture entitled Dynamics of Small Particles in Flow. And with this brief introduction, I will now invite Dr. Rama Govindarajan to please come over to the dais to deliver her talk. Dr. Rama Govindarajan. Who would like to do something?
It's a very big honor for me to speak in a lecture named after the eminent particle physicist you've heard about, Professor Bibha Chowdhury. And so I'm deeply grateful to PRL for this opportunity, especially Professor Bharadwaj, the director, Professor Raju, Professor Deshpande, and a very big thanks to Professor Shubhavati Goswami for this opportunity. I will be failing in my duty if I do not mention
something about women in science before going on to the lecture. So this is actually a quote from Bibha Chowdhuri in the Manchester Herald. So somewhere in the 1940s, she had given this interview. And yeah, like even today, we could do better with more women, but it's of course a lot better than in her time. And yesterday's APS Physics magazine, in case you have not seen it, I will encourage you to read this thing about how they say there's still bias in the system against women scientists. I also want to add that though things have become better for women today, there's a lot of other minorities of different gender identities, for example, which need a lot more attention. And even for women scientists, it's gone from, let's say, blatant discrimination some decades ago to covert bias and unconscious bias, even among people who believe they're not biased. So that is what came out yesterday in the APS Physics magazine. So she was a particle physicist of great eminence. I'm speaking about small particles in flow. It's particle physics of a lesser kind, you can say. Okay, so what are we studying here? We're studying small droplets and small particles in flow. So here are some examples of particulate flow. Once you realize, once you look at some of these pictures, you'll realize that particulate flow is everywhere, and we really need to understand particulate flow to understand so many aspects of physics. And so in order to understand particulate flow, I'll explain, today's whole aim is to show why it is a hard problem. And if I can convince you that it's a hard problem and worth answering, and if I can tempt some of you to look into problems of this nature, then I'll be very delighted. So yeah, we've studied a lot about particulate flows in the COVID context recently, and you've seen these situations. Marine snow is something very important which I want to mention. So basically, you have small plankton which live somewhere in the upper ocean, and they are responsible for grabbing a lot of the carbon dioxide from the atmosphere. Like we bad people put carbon dioxide in the atmosphere, and these nice people, the plankton, they try to help clean it out by grabbing the carbon dioxide from the atmosphere, and then their dead bodies and fecal matter sink to the deep ocean. So how much of carbon dioxide can be sequestered into the deep ocean depends on the sedimentation of marine snow. Clouds are something we'll be talking about in some detail in the coming slide. There's so many other situations like river sediment. And yesterday when I was flying into Ahmedabad, I saw one of the tributaries of the Sabarmati with amazing meanders. And these are caused by particle deposition and erosion. So now what is so complicated about particulate flows? So first of all, we know the equations. So what can be so complicated when we already know the equations which will solve them? We're not, doing some rocket science here. So the Navier-Stokes equations, we know. And if we can apply the right boundary conditions, we can solve everything, right? So my idea is to show that that's not just the case. So first we know the equations. What would we normally do? We have a bunch of differential equations. We would discretize those, and we would draw some kind of grid on which we discretize the equations, and then we'll apply the right boundary conditions. Here I've drawn one particle, one dust particle in a dust storm, or one teeny water droplet of 10 micron in a cloud. The first thing I want you to remember here is the single word turbulence. So in all these flows are hugely turbulent. Any large flow is going to be turbulent, and that's when the whole problem starts. So we're solving Navier-Stokes not just for anything, but for turbulence. And so we apply the boundary conditions and we'll solve the difference equations. Even if it's turbulence or if it's lamina, whatever it is, we know the equation. So the key in turbulence is that we have to choose a grid whose size delta x is small enough And therefore, the time step we take has to be correspondingly incredibly small. So if we can resolve it beautifully, for example, here I've drawn one dust particle and I've drawn a bunch of grids around it. So if we can put that many grids into the flow and solve it, then we're done. But we cannot. So like just to talk a little bit about turbulence. So every cloud is turbulent. They're turbulent to varying degrees, but typically even before you're entering a cloud patch, when you're flying, the pilot is going to switch on the fasten seatbelt sign. So it is going to be turbulent. So when I'll encourage you next time to look out of the window when they put the fasten seatbelt sign, and you'll see typically clear air turbulence is rarer. You'll typically see that you'll enter a cloud patch. And now in this cloud patch, if we could solve the equation, we know that, at a given time, like, cloud cover can be 10,000 kilometers. It can be like seriously as big as the earth. So like if we want to solve for the whole cloud, or even if I take an individual cloud, which can be about 1,000 kilometers in one direction. So like there are, this big scale things happening, and there are small scale things happening. And here I've drawn the order of a meter. Inside a meter, you see turbulence looking like this. This is vorticity, the curl of the velocity vector. And you can see that it has different intensities, different lengths. So you can think of it as a bunch of noodles of different radius, very long noodles who are, making each other move. These vortices make each other move around. So vorticity is typically in these, rod-like patches. So like that is an important thing to remember about the nature of turbulence. And so if we could, in fact, see this little patch in the cloud, we would see this. If we could plot del cross U inside this patch, we would see exactly this. So the scales of these vortices can be huge, like they can be kilometers or many kilometers in size, and they can be sub-Kolmogorov. Kolmogorov is the smallest scale in turbulence, which is no longer the smallest scale. We now realize that very important things are happening at a scale much smaller than Kolmogorov. But we can think of Kolmogorov as the scale which was thought to be the smallest. So we have vortices which are even much smaller than Kolmogorov. And the picture shown here is a Johns Hopkins simulation, which is actually a pretty weak simulation compared to what will be happening in a real cloud. In a real cloud, the intensities will be much, much bigger. So now the point is it's a nonlinear system. It's a chaotic, terribly scary, terribly difficult nonlinear system. And in a nonlinear system, every scale forces every other scale. So the small scales put force on the big scales, decide what the big scales are going to do, and vice versa. Obviously, we cannot solve for all of these, and I'll explain why in the next slide. So the first thing we do is we decouple. We pretend that the small scales and big scales can be computed independent of each other, which they cannot. This is the first pretense. We are solving for the big scale separately, small scale separately. And then we are trying to, put some forcing by hand of the small scale on the big scale and big scale on the small scale. So we are doing something empirical and not quite correct when we decouple the big and the small scales. So that's the first thing. So we've already split 1,000 kilometers into different boxes of about a meter. And we're pretending that, whatever is happening in the meter is independent of what's happening in the big scale. So that's the first thing. So now let's accept that we are solving for this teeny little, patch in a cloud. So here, the biggest Navier-Stokes simulation which has been done, and it's simple Navier-Stokes, not including thermodynamics, not including many things that happen in a cloud, has about 16,000 grid points on one side. 16,000 grid points on one side. And that's the biggest. It's been done on lakhs and lakhs of computers connected in parallel. If you're going to go sub-Kolmogorov, you're going to resolve about a 2-meter box. So this is where we are. We're solving for a 2-meter box in a cloud. And that's the biggest simulation. Like we in India are too poor to go anywhere near it. So then we looked at this biggest simulation. And in this biggest simulation, let's assume we got all of it. We see those vortices that I showed you in the previous slide. Now these vortices as they grow smaller, as they go smaller and smaller in size, there's a teeny tiny population of incredibly small vortices. But here, all your usual dynamical, your analysis based on the dimensions is going to go wrong, because this is a very multifractal system where these teeny tiny vortices are incredibly intense. So I tried to show that by dark pink compared to light pink. So as you grow smaller and smaller in scale, you're going to become more and more intense in the vortex. So like here we are, we've drawn a grid like this and we are solving for the teeniest vortex in the flow. And you can now compare how big the particles are, how big the droplets are in a cloud or particles in a dust storm compared to our grid. So if we were solving it right, we would actually have to put a little grid around the droplet or around the particle and put the boundary conditions there and then solve it. But we have absolutely no way of doing it. It's way smaller than a grid. So what do? We cannot do this. And here itself, we've decoupled from the big scale. So we've done many levels of approximation where we are missing a lot of physics. And in fact, in monsoon clouds, yeah, this is the summary. 10,000 kilometers to 0.1 millimeter. That's also not enough. There's 10 to the power 11, and there's like 1,000 droplets per centimeter cube. So like if but just solving the flow, forget the particles. And that's impossible. And we saw that it's even more impossible to resolve the flow around each particle. So here we do another level of decoupling, another level of pretense, or we can only try our best, right? So we're doing this. We say that these droplets are too weak to disturb the flow in a cloud. And so like we'll only model the flow on the droplet. We'll solve for the droplets separately by decoupling them. And we'll ignore the effect of the droplets on the flow. I'll show you a reason why this is not great. And then we'll also ignore the effects of droplets on each other. For now, we'll again see why that's not great. So we're doing like many levels of approximation, each of which is missing a lot of physics. So there are big open questions at every level and every length scale and every stage in this game. So like when we're putting in a lot of stuff as semi-empirical parameters, so we're solving, something for each individual. Putting it back as parameters into climate models. So we are getting it wrong. So like in some cases, like when it's far away from the equator, somewhere in the high up in the northern hemisphere, they get these things a lot righter than we do for various reasons, partly because they have more data and they can keep correcting these empirical things using the data. So more of that kind of thing needs to be done for the monsoon system. Okay, so let's go back to the fundamentals. So here is the Navier-Stokes and the continuity equation. U is the flow velocity, P is the pressure, R is the Reynolds number, RE, which is some velocity scale times some length scale divided by the kinematic viscosity. And in clouds, this number is very, very big. And as the Reynolds grows bigger and bigger, we need more and more grid points to resolve the thing. That's where the hard part comes. So this, like, and forget the droplets, but just for the flow, we need many, many more grids. So that's about the flow. Now the particle, the thing that we pretend right now or we consider right now is that all particles have extremely small Reynolds numbers. So there's a flow Reynolds number and a particle Reynolds number. The particle Reynolds number is based on the relative velocity between the particle and the flow and its size. So you say you're considering particles only which are very, very small, such that their Reynolds number is very close to zero. Under this condition, you can write an equation for each particle, which looks like this. It's the Maxey-Riley equation. So Q is the relative velocity, V is the particle velocity, U is the fluid velocity. And this equation works only for a perfectly spherical particle. And we know that a lot of particles are not spherical, like ice particles in the cloud are not spherical. So many things are not spherical. So like the particle's position y dot is V and q is v minus u, we can write an equation for v minus u. And it has two non-dimensional numbers, one which is based on the density ratio of particle to fluid, and one which is called the Stokes number. It's a time constant ratio between particle and flow. So it's okay if you don't get this whole equation, but just pay 1 minute attention to the thing shown in pink. This is called the Bassett-Boussinesq history. We will be talking very soon about this. So I want to drive home the point that here we are, there are quadzillions, some infinite number of particles in all these big flows, dust storms and things like that, and clouds that I told you about. In a cloud, it's like 10 to the power of 9, like 1 billion droplets per meter cube. And to solve for each droplet, even if we are assuming it's zero Reynolds number, you get this incredibly complex equation. And this equation is only approximate. So that is the level of complexity we are driving at. So what do we do? Like, what do we do when this is like this enormously unsolvable looking problem that we are confronted with? We have to think of clever ways to reduce it. So we think of clever ways to solve little portions of the thing and cull out some physics. That's the whole idea. We start by culling out the physics in pen and paper work. So we're happy that we could do, I'll show you 2 examples of this as we go along, that we can do pen and paper work and pull out what physics we expect. And the next thing is to write down some even more complicated equations, which we may not be able to solve on pen and paper, but we can write down with pen and paper. These are subsets of the Navier-Stokes and subsets of Navier-Stokes, including droplets, things like that. So we write those equations and then we can solve them analytically or numerically, but they'll be ordinary differential equations or simple partial differential equations, which we can solve pretty exactly numerically. And there, like, we can again reveal some extra physics. For example, asperitas cloud formation, which I will show you. And then, like, you know, how do particles interact with each other? So things like that we can solve analytically or numerically. And then we do large simulations. Like I told you, we're not doing anywhere near the large simulations we need to be doing. I don't think there's a replacement for that. We should be aiming to do larger and larger simulations. But some of the physics we can get, and we are happiest if our large simulations are primarily confirmatory of our basic physics. So then we know that we've hit onto something. Okay, so the Maxey-Riley equation, I told you we'll come soon to this equation and talk about the Bassett-Boussinesq history force. This force is usually dropped by everybody who does, you know, big particulate flows. They say, okay, like we can't do it, so we drop it. So they don't have evidence. We still don't know very clearly, like when it can be dropped, when it should not be dropped. We know that in the Stokes number, if the Stokes number is small, it's not always small. But if it is small, this has a square root Stokes in the denominator, this has 1 over Stokes. So we can just compare it like by I to this term and say, oh, this term is going to be big and this term is going to be smaller. But that's not the case. Like that's not often the case because the coefficient can grow and grow. So like we drop this, it's usually dropped, but it should not be dropped. That's the moral of the first part of the, first example that I'm going to give you. So yeah, I'll be quickly going through these examples and not giving you the details because I have to finish in some time. Shubha, how much time do I have? Half an hour? Okay, I'll try to do even faster than that. Okay, so this force, just take a look at it. There's one term here which is 1 over root t, which is a singularity at time t equal to 0. There's another term here. Q, remember, is the difference between the particle velocity and the flow velocity. There's another term here, which is an integral going from 0 to t at every time t. So this means I have to go back in time. I should remember the way the particle was accelerating, the way the flow was accelerating, and take the difference between the two. I have to store that for all time from 0 time to now, and I have to make this integral. So I have to calculate this integral. Then I go to the next time step. It doesn't help. I have to go all the way back to time t equal to 0 because of the denominator. And then I repeat this integral. So as my time goes on, at every time step, just to calculate for one time step becomes slower and slower and slower. So I hope you can imagine what's happening here. So no wonder people just drop it. And we started looking at this problem, and my colleague Vishal has been the genius in this brilliant idea that I'll tell you. So the main worry is it's not a dynamical system. In other words, if I know the system at time t, I cannot get the system at time t plus delta t. I have to know the system at all times before and do this elaborate calculation. So what Vishal said is the following. So we knew that this whole thing, if you go back to your analytic functions, and your Riemann calculus, you will recognize this as a half derivative in time. It's a fractional derivative in time. So that part was recognizable, but Vishal's genius was to say, okay, like if something is a half derivative in time, why don't I write a fictional heat equation in a fictional variable x? And then the half derivative in time will become a single derivative in x. So this is a very, very nice simplification that he could do. And normally, like what do we learn in school or college? Every time we see a partial differential equation, our knee-jerk reaction is to say, is it variable separable? Is it this, that? Like we're basically trying to make it into ordinary differential equations, right? Everybody must have done this thing of trying to make a partial differential equation into an ordinary differential equation. Well, Vishal did the opposite to simplify it. So that's what changed the way the equation could be written, and we could make a numerical method, and it's no longer a dynamical system. That's the magic. So we get everything at time t, and we store the entire history in a few Fourier modes. So that's the, yes? Excellent question. So I should say that we are talking about particles which are bigger than a micron. If they're smaller than a micron, then Brownian motion is very, very significant. So like what happens in clouds is no particle stays smaller than a micron. Most of them grow very quickly to 10 micron because of condensation. So we're dealing with particles of the order of some microns. But if we're dealing with extremely tiny particles, then we'd have to account for Brownian motion, no doubt. By the way, if there's any questions, please feel free to stop me. I don't have to get to the end of my talk. I'll be happy to answer questions and stop anywhere. So it's just a few examples, so I can stop anywhere. You mean when particles collide and scatter? Yeah, we have to account for that, but it's typically ignored. Typically, people say the system is too dilute, so let's not worry about those isolated collision or scattering events. But typically, you could have in collisions, you could have coalescence when it's water droplets, or they could just dash off each other, or ice particles could agglomerate to make a bigger thing. So we have to do the details of the interparticle dynamics when they come closer together, but it's impossible to do. So we have a method which is numerically better for a general system. That's the moral behind this. So like the other computation time keeps growing with time, but ours like, doesn't, it grows linearly. That means each delta t is taking the same amount of time. Okay, so why is this important? Like, is this Bassett history important? So let's go back to, I was going to say high school, but probably it's JE coaching where you first see it. So in JE coaching, you look at a small, teeny tiny drop, which is a particle. So like you take a tiny particle and in Stokes' flow, you're dropping it on the top of an ocean and you're allowing it to go down. The ocean is still and the small particle is coming down. This is the trivialist example of an unsteady Stokes flow. where you're dropping this particle, it has reduced gravity. That means gravity minus buoyancy acting on it downwards, and it has a drag acting upwards. So this is gravity minus buoyancy, and this is drag. And I put Q for the velocity, where Q used to be V minus U, but U is 0, so it's just Q. There's a time scale you can write based on the particle's radius A. And now this is the equation we used to write down when we were in JE coaching. And this is a first order equation. You solve it, you promptly get Q is equal to reduced gravity times tau, the time scale, into something which is basically this thing is going to drop out. So you're going to reach a terminal velocity, gr times tau. So this we've all solved at some stage or other. But wait, this equation is wrong. We neglected the Bassett history term. And now the correct unsteady Stokes equation is with the Bassett history, and which we've written in terms of that fictitious variable x right now. So it looks all simple, but it isn't that simple. So this is the equation we should be solving for this teeny tiny particle which is falling through the ocean. And when we solve for this, I'm very happy to say that we got a bunch of analytical solutions, like pen and paper solutions. And this is the first time that, to my knowledge, that we have a first complete analytical solution for a little droplet falling under gravity. So again, Vishal's genius on how to transform it. But once the idea is there about the partial differential equation, we can do this. So it looks messy, don't worry. This is the answer. So Q is, again, at infinite time, it's going to gr tau, the terminal velocity. But it's going algebraically, it's going very, very slowly to that terminal velocity. Whereas the previous graph you saw, it was going exponentially fast to the terminal velocity. So this is a crucial difference, which is that the unsteadiness cannot be quickly forgotten. The unsteadiness is algebraically decaying, which is way, way slower than exponentially decaying. So that is a common thing which Bassett history does to every particle in turbulence. It does it all over the place, and there's many, many consequences coming out of it. So like for the general case, we have this method for a constant memory cost and far, far better computational cost. And we can solve problems like this, where a big droplet in rain is coming and collecting small droplets. And we see that without Bassett history, we would overestimate the size of this particle compared to what the Bassett history gives us. So this is actually a particle with 10 times the density. With a cloud particle, the effect is smaller, but in many situations, the effect is very big. So this is one example of pen and paper work, which can then, we can think of learning from this using AI and then putting it into bigger simulations. So we're still a bit away from that goal, but that would be the long-term goal, where all physics could be incorporated better into this problem. Another example is we now go to the baby form of the Maxi-Reilly, where we are neglecting the Bassett history just for demonstration. And we look at what happens in the neighborhood of a vortex. I told you that turbulence has all these vortices, which are often, cylindrical in shape. They're not always cylindrical, but one of the things they like to be is cylindrical with a Gaussian profile. So when we take one such vortex, and, we saw that that vortex is the grid size, but the particles are far smaller. So let's solve analytically for just particles around one single vortex. And due to centrifugal action, because these particles are denser than the fluid, the neighborhood of the vortex will get voided. And this voiding is very important for collisions. And collisions and coalescence are very, very important for rain formation. So one simple moral is, and I think most people in the community accept this, no turbulence, no rain. This coalescence of droplets due to enhanced collisions due to turbulence is crucial for rain. So like that, you can just see how these things get voided. And we have a simple formula, pen and paper formula for what is the radius of the void. So once we know the radius of the void, we can compute the complete void volume in the turbulence, because we know the distribution of vorticity in a turbulence. We know everything statistically about turbulence from not our data, but Johns Hopkins, the big 16,000 and 8,000 kind of data that I showed you. From there, we know the statistics of these vortices, And knowing the statistics, we can by pen and paper get the total void volume. And from the void volume, we can get an estimate of the collision. So it's not like, the usual kinetic theory. We have to do something a little more sophisticated to estimate the collision kernel. And by pen and paper, we can get how much collisions, and therefore, how much vorticity do we need to form rain? So how much Reynolds number do we need to form rain? So we came up with a number about this in this paper last year, which we say is something like a hand waving estimate for the minimum turbulence in a cloud that can cause rainfall. So this is the next example I wanted to show you. A cloud, of course, is a much more complicated problem. We actually should not be using the simple turbulence simulation. We should be doing a simulation where we include many of these effects, in particular evaporation, which is going to change the temperature profile, evaporation and condensation. And that is going to create buoyancy. So there's a lot of things that are ignored in this hand waving estimate. So we may have got it wrong. But it's the beginning of trying to understand what turbulence does for a cloud. So this is a visually pretty example which I wanted to show you. So this asperitas clouds, how many of you heard about asperitas clouds? You have? Oh, great. So this is the newest cloud that's been designated by the World Meteorological Organization. So like after many, many decades, they actually recognized a new kind of cloud in March 2017. So it's exactly 6 years since then. So this is a pretty young cloud, or it was always there, but it's at least been given a name and an identity pretty recently. So then this is the characterization of that cloud. And here are some pictures by cloud watchers about on the asperitas cloud. So you see that there are pointy things, and there are, these striations which seem to have some organization. And this is what the cloud looks like. So for this cloud, we could actually write a simple mechanism. And the mechanism was as follows. We said that as droplets, so here's the bottom of the cloud, and the droplets are sinking from there because they're falling under gravity. And they're evaporating just below the cloud. And wherever they're evaporating, that place gets cooled because of latent heat. And so like now you have a cold air layer beneath the cloud and everything is still. We add a shear to that for this asperitas. And this cold air is denser than what is below. And we know that whenever something heavy is on top and something light is below, you get instability, you get baroclinic torque, you basically get the Rayleigh-Bénard kind of instability. So then like that is the mechanism we proposed for this. And because we caught the cloud early, there was only one paper before us, this Harrison et al. On this cloud. So like, yeah, we probably have written the second paper about this cloud, but I could be wrong. So then here is a movie on the cloud formation. Remember I told you in the beginning that, we write down these equations, we wrote the stability equations, we derived conditions for this kind of instability to take place. But we could only derive those conditions. In order to see the cloud visually, you need a full simulation. So here we've done a full simulation of this cloud. And you start seeing the kind of asperitas formation. It's kind of short-lived because it goes into turbulence later, but for many minutes you have the asperitas. I'm just playing it again. It's not playing anymore, but you saw the thing, like if you saw that we could basically get the shape of the thing. Go back once more. Yeah, so as these droplets fall, we are moving down with it. You can see like some similarity. So at least we think we've got a mechanism, we may or may not be right. So you see like with the first figure, you can see, and then it dissolves into turbulence. At very long time, all the droplets evaporate and there's no cloud left. But for quite some time, you'll see this kind of behavior. Simulation time. It's on a parallel thing. It's done parallelly with maybe, I can't remember how many cores we use. Oh, actual time. okay, we have cheated. We've got a Reynolds which is much lower than the actual cloud. So like we've got the gross mechanism right, but there's no way we can compute it that Reynolds number. So our simulation time, it's still not too bad. Like it's like a few minutes, whereas this cloud may form in tens of minutes. So yeah, it's not too off, but we can't claim that we've got the time right. We've not got many things right, but we think we've got some physics right. So this was done on a 1024 cube box, which is actually like we're not resolving many things as you mean. Then we come to interactions. We are now pretending till now that particles don't talk to each other, but we know that, when particles come close, if you want to do collisions right, you want to resolve the hydrodynamic interactions when they come closer. We're nowhere near doing that. We'll still pretend that these are point particles which are far away, but even point particles have forces given to each other. And then like what effect does that have? So this, I'll just walk you through a bit of Stokes flow, and this can be solved by these things called Stokeslets, where you're putting point forces for each particle. So if there are two of them just placed here, they go at a terminal velocity, but that terminal velocity is faster than gr tau. They're going to finally go at long time faster than they would do individually. So each thing pushes down its neighbor. So that's the kind of thing. And if they're one below the other, they go down even faster. So there is the old terminal velocity and then a factor which is something related to a by d, where a is the radius and d is the distance. So if they're very, very, very far away, then the correction is small. But when they come near, the correction is big. So this is something that happens with two spheres. If the two spheres are at an angle, they not only move down, they also translate this way. So that's very interesting, like two things settling under gravity, but they're also going sideways. So they actually fall like this. So that is what happens. And now when you have three spheres, something very interesting happens. You have like two of them trying to translate this way, two of them trying to translate this way. And as a result, these two come near and the middle guy gets pushed down by both of them. So it falls down faster. So already you have an instability, and this instability brings particles closer. So this is the famous Crowley clumping instability. I'll show you a movie which Rahul made with just 5 particles. You can see the clumping that happens. This is an experiment. He's dropped this into silicone oil. And now, like he did, like Rahul did many more experiments for, ellipsoids, like disc-like particles. We start them out with a small perturbation and we ask, is it stable or unstable? Spheres are always unstable to Crowley. That's the thing that I showed you. And here, and Harshit is continuing this work with 2 colleagues, Sriram and Narayanan. Harshit is continuing this work theoretically, whereas Rahul did it primarily experimentally. And we made these discs just fall in a line. So this is just the simplest thing we can do. Like if we can do pen and paper work on it, we can understand how clumping happens in this. So we can understand everything about clumping in this very simple experiment. These are 3D printed little resin discs. So like what basically happens is that Crowley says, all of you are trying to fall like this by the mechanism I told you about. But when you have things which are not spherical, then what happens is that this clumping is fought against. So every time this particle comes down, it actually turns around, and this orientation makes it move that way. So while Crowley is clumping them, the orientation is pushing them apart. So you have these stabilizing influence of the particle orientation. So this is a result we found. And we can do a stability analysis. Don't worry about this messy thing. Just look at this. There's a wave number of perturbation and the spacing d by a. This part is all stable now, which could never be stable for a sphere. And the dots are experiment and the blue and pink coloring is theory. So we see like amazing, agreement between experiment and theory. And in the stable regime, it's still unstable, but it's unstable in a different way, which I'll come to. And this is the unstable region where clumping happens very, very fast. Okay, so I just want to leave you with this last thing, last basic concept, which is the following. So like whenever we have a system and we are asked to tell whether it's stable or not. So like a ball placed on top of a hill or a ball placed at the bottom of a valley. What do? We perturb it in a small way from its equilibrium position. And then we write a simple linear equation for the perturbation. We say the perturbation is so small that perturbation square terms can be thrown away. We write a simple linear equation for the perturbation and we look for the eigenvalues. If the eigenvalues are all negative, we say it's stable. And if the eigenvalues, even one is positive, we say in some direction it's unstable. So this is basically what we do when we talk about stability analysis, right? Well, in fluid mech, we have to think differently, and probably in many, many situations, we have to think differently. So this is an example there. This is an example there, and in the simple disk system, we found it, but it's there all over the place. So here is the original eigenvector 1, and here is eigenvector 2. And important point is that because the stability matrix is not self-adjoint, it doesn't satisfy this thing, the eigenvectors are not orthogonal to each other. Normally in quantum mech and in many situations, you'll always have eigenvectors which are orthogonal to each other. But when they're not orthogonal to each other, see what's happening here. So this at black is at initial time, 2 eigenvectors, and based on their eigenvalues, they both decay. So pehle the black resultant was this little arrow, and then both of them decayed to these red things, but the red resultant has grown. The resultant has grown while everybody is decaying. And this will happen only for a short time. At long time, everybody will decay to 0. But in that short time, you will get algebraic growth, not exponential growth. Here's another example in a completely different context. We saw in the Bassett, you saw algebraic attainment of algebraic dynamics and not exponential dynamics. Here again, you'll see algebraic growth of perturbation. So that's what happens in our stable region. And the interesting thing is this is well known now for 3 decades in fluid mech, that you can get algebraic growth pushing a flow from laminar to turbulent when every analysis tells you that the laminar flow is stable. But it's very, very difficult to see this thing in an experiment. And here we've devised a very simple experiment where we have direct confirmation of algebraic growth. So this is, I'll just leave you with the fun movies. So this is actually the dabba where we did the experiment, and this is a close-up of it. So you can see this beautiful instability growing. It's just visually very nice. And I mean, I've shown you this in 1 second, but to see it in our lab, like you'll have to drop those discs, then go for chai, come back. It would have done a little, then go for another chai, come back, and so on. So like, yeah, it takes a long time. It's Stokes flow. What? So it's just a box like this size. And in that box, we 3D printed little bits and put them. And then we 3D printed these things and left them there. And the box is filled with silicone oil, which has like 10,000 times the viscosity of water. So it is very, very, very slow. So it's like dropping it through honey, which is even more viscous than honey. That's it. So we just let it drop and we go away. And we take a slow movie. This is actually a movie. No, there is no steady state. Either you get algebraic growth or you get, exponential growth. So there's no steady state. The only thing is you can slow down the transient growth a lot by choosing some parameters. So you can do that. And I mean, like this looks like a very easy experiment, but it's actually a very hard experiment. And I'm really, really proud of Rahul Chajwa for, solving all the problems we came across on the way. Like we had to devise a method which would very neatly push them down. We had to devise a method where we could actually give a teeny, almost sinusoidal perturbation. A lot went into this experiment, but we were rewarded by this very nice final result. And in the neutrally stable regime where it's algebraically growing, so if you run a thing there, you'll see like perturbations growing there also, but you'll see like very gentle perturbations. So experiment by Rahul, simulation by Harshit. And of course, it's a chaotic system. It's very non-linear. So you cannot expect a one-on-one agreement. But the statistics is like perfectly got by our simple theory. So should I run this again? You see, in fact, these pairing up and funny kind of instability, not the other clumping that you saw. So the way these particles are going to interact is very different in the stable and unstable region. This much. 5 millimeter, 3 millimeter, like that. We've made different sizes, but yeah, few millimeter. I'll just show it once again. Sorry, disk. This stable region doesn't exist for spheres. Spheres are always unstable. It's only when you have these disks that, you know, the orientation fights with the tendency to clump. The orientation pushes them apart. So they're able to resist clumping a little more. Disk has a finite thickness. It's basically a spheroid. It's not a flat disk. So we model it like this simulation is done on an ellipsoid with some small a by b, like small b by a. Yes, but it's not a simple power law. It's not a simple power law because you have in this system, in this simple system, you have 3 eigenvectors, which can give algebraic growth, which is not a simple power law already. And in most fluid systems where laminar is going to turbulent, you have like thousands of eigenvectors. And each of them like, and it's only algebraic in pairs for a short time. So it's not going to be one simple power law ever. Although you may approximate it by some kind of power law. But you're right, the dynamics is slowed down to power law behavior from exponential behavior. Overall dynamics is slowed down and you get this growth for quite some time. I cannot predict the individual, behavior of each particle. That depends on, teeny tiny errors in the way we've placed it and things like that. So once it enters the nonlinear regime, I cannot predict it. But the linear regime, I can predict very well. And from the linear regime, the nonlinear follows. Like you get a completely different nonlinear behavior because the linear is stable as opposed to unstable. Yes. In the medium, yeah, then you'll not get this clean thing, but you will get something similar. Like if there's a problem with the walls or the thickness. So I mean, in our system there is inhomogeneity, although we've tried, but in a system which is far more inhomogeneous, you'll get a different kind of clumping. You won't get these clean waves, but you are going to get some signature of this. It's not very narrow. The wall, it's like this much and the particles are this much. Yeah, it's like we keep the AC at 22, something like that. But it's not beautifully, but we try to keep it like that. So it's just a general AC in the room and we have temperature, whatever accuracy you can read. It's not like fantastically controlled or something. So like before I conclude, I'd like to show my past PhD students. All of these are in permanent jobs as faculty in different places. And some of these have recently joined as faculty and these people are all postdocs, and this is my present group. I showed you some work of Saumav and Divya on the Bassett history, and I showed you Harshit's work on the interacting particles, and I didn't have time to talk about many of these people's work. So like these are the people with whom I really enjoy working all through the day. They always, put me on exam mode, like they're always testing me, and this makes me get better. And I have them to thank for this opportunities like this where I can stand before you all. So this is my conclusion slide. So basically, I wanted to send you the message that solving for even a single particle correctly is hard. Remember, we were talking only about Reynolds going to zero, but if Reynolds is not going to zero, there's million other problems. And remember that they're in extremely large number. I don't think there's even a name for that number. It's some quadzillion, that many particles are there. So we need to do this better. Assuming steady state by ignoring Bassett history can be a bad move in many situations. The void formation is important for collisions. This is a thing that we showed, like we believe that this can trigger rain, and we got a Reynolds number which could, stand in for the onset of rain. And we know that a majority of clouds don't rain, so we need something more. And this was for a particular number of droplets and so on. Stability analysis can yield very nice things like the asperitas cloud formation. The important thing is particles affect each other and the flow. And we have only talked about particles which are still far away from each other, where they're like point particles to each other. We haven't even talked about when they come close together. So there's a lot more that needs to be done in this problem. Thanks a lot for your attention.
Thank you for this very fascinating talk. With a lot of aspects, you introduced us to the big problem that exists and the importance of it, and also the magnitude of the problems, right from small scale to large scales, and how you and your group are trying to break it down into smaller problems to address this. Very interesting. Thank you very much for this talk. And I'm sure there are questions, but I'll request our colleagues to please wait for the mic, because only the questions asked in mic will be heard by or recorded in the YouTube. So please wait. Yes, Neeraj. Wait for the mic, please.
Okay, first of all, thank you so much for such a nice talk. And since you talked about theory, but with the picture, so we could follow many of the things. Okay, my question is related to, you started with turbulence. And then one of the slides you have shown that aerosols going to raindrops. Through turbulent, they are forming clouds, and without turbulence, there are two pathways you have shown. So what I could not follow there, what is the source of turbulence?
Okay. So the point is that for a cloud, in all flows, the source of turbulence is finally the large scale. But for clouds, I can tell you in a little more detail right away. So you have the ocean or some water body, and the water is evaporating on a hot day. So this water is evaporating. It's already lighter than its surroundings because it contains water vapor, and it's a little warmer. So it starts climbing because of buoyancy. So it climbs higher and higher and higher. So now imagine a big parcel which is climbing. So that's like a plume. And a plume goes turbulent at a Reynolds number of 5 or 10, something of that order. So like already a plume of this size will be turbulent. You cannot keep it laminar. For example, you light a candle and you'll see the plume above it is already turbulent. So any plume like that is going to be turbulent. So the source of turbulence is just this, but you can think about it even better in a cloud where you have potential energy, because as this thing is rising, it's sacrificing potential energy for kinetic energy. And then as the droplets start condensing, first of all, it had water vapor, and now it starts getting droplets. So then the latent heat is released and this thing becomes warmer. And so now chemical energy is converting to more potential energy, which is converting to more kinetic energy. So anything that has big kinetic energy is turbulent. Not all clouds are turbulent in the same way. Some of them may have weak turbulence. Their Reynolds number may be smaller. So depending on the convection, depending on the size, depending on, how patchy they are or how easily they break up or how fast they dissipate, their Reynolds number can be different, effective Reynolds numbers.
Okay. Thank you. We'll move on to the next one, Professor Bharadwaj.
Thanks, Rama, for an excellent talk, and it was really educative to many of us to understand the nuances which you're trying to simulate as well as mimic them in the experiments. I have a couple of questions. One is, when you're talking about clouds, you're applying simple fluid dynamics,
Yes.
right? But clouds have charges. So
Yes.
are you accounting for electrical forces?
Yes. So we are not. As it is, the problem is hard enough. We are actually ignoring electrical forces, which is bad. We are ignoring upward convection, which is bad. We are ignoring Earth's rotation, which is bad. We are ignoring many things. So yeah, it's on the whole bad, but what do you do? It's that kind of thing. And this thing about charges is very interesting because nobody understands lightning. And people are only beginning to start studying it. Nobody understands why there is charge separation, why charge separation is a function of height, and how it suddenly discharges. Okay, when it's big buildup, it discharges, but it's an open problem. It's an open problem, at least from, including the fluid dynamics and doing it that
I
way.
will. I will talk to you later on this issue. The second question is, when you're talking about clouds again, cloud formation happens on CCNs, cloud condensation nuclei.
Sorry?
Cloud formation happens on CCNs, which is called
Yes,
cloud
yes.
condensation nuclei.
Absolutely.
How do you simulate that?
Okay, so what we do is that we take a number of particles per volume, which are our cloud condensation nuclei. And then we use standard Clausius clapeyron to give you deposition on each thing. And we track actually how the radius of each of them grows. So at 0 time, they're made up of something else, maybe not water, but as time goes on, they due to deposition of water on their surface, they become effectively a water droplet. So we just solve it by Clausius clapeyron.
How much time it takes to grow?
So when you're starting, suppose a cloud is just starting, there's a lot of cloud condensation nuclei in the atmosphere, and let's say some convection has arrived at that height, then it takes about 5 minutes. It takes 30 seconds to reach till 10 microns. So the initial growth from 1 to 10 micron on the right kind of aerosol particle is 30 seconds to a minute. After 10 microns, it flattens out a lot. So then to reach till, let's say, a millimeter by that process will take order of many days, weeks. So you cannot grow only by supersaturation after 10 micron. After that, you need turbulence, you need some other thing.
See. And these are the clouds which are simulating is like deep clouds or simple clouds of different characters?
Okay, so we are trying to simulate deep clouds because we're putting a lot of supersaturation and things in that. But because usually the deep clouds are the ones with 5% supersaturation and things, but that's just to make our simulations faster. And again, we're not simulating deep clouds because we're solving for this little box, which we're saying is homogeneous isotropic, which is not the case for any deep cloud. So we are simulating some aspects of deep cloud.
Last question. What is the lifetime you're looking for the clouds?
Lifetime. It's about an hour in real life. If you, okay, so suppose you have a video camera, you leave it on the terrace, and you will see that in every 5-10 minutes it's changing, and certainly nothing is going to last more than an hour, the typical cloud. It will be replaced by other clouds in the monsoon time, but yeah, a given one is about an hour. And rain forms within 10 minutes.
So your simulation which you're doing is also lasting for an hour or half an hour kind of thing?
We are not simulating for that long, and we are simulating at lower Reynolds number. So I mean, our time scales will be different from the cloud time scales.
Okay, so fast simulating it in that.
Yeah.
Thank you.
And that's just because we don't have a powerful enough computer, that's all. Like I mean, our code is running on this many parallel machines, but if we had like 1 lakh parallel machines, then we could make the grid finer and we could push up the Reynolds. So like if we run at a high Reynolds with a smaller grid, we are cheating because we're not resolving the small scales, and that's what we're doing.
Okay, Professor Deshpande.
Thank you, Dr. Rama, for very nice talk. And I say so because I'm a geoscientist and I understand very little of physics and so much about questions which I'm trying to link and connect with geosciences. Let's begin with first question, which is for you, it is very simple. That how do you define this delta x of Kolmogorov? Well, you said that delta x has to be much, much, much smaller than the delta x of Kolmogorov.
Yeah.
So how do you define it?
Okay. Okay. So this idea started from Kolmogorov 1941. There's a famous K41 paper. And in that paper, he said that viscosity is unimportant when the Reynolds number is very high. So in turbulence, for the big scales, big eddies, they don't care about viscosity. There is an energy cascade, like the big eddies, they feed their energy to the small eddies, and that's how the big eddies dissipate their energy. And the smaller ones feed into an even smaller ones, and so on, all the way down to very, very tiny eddies. So this was a simple picture of the energy cascade. And that happens every day in our life also, like when we switch on the washing machine. There's one big drum which rotates or a big blade which rotates. So we are putting energy on a big scale. But if I could go and take a video thing of it, I'll see vortices at all scales. Otherwise, our clothes are not going to get clean, right? If everything just went around in solid body rotation, that's not going to work. So we actually need turbulence. So like when you go smaller and smaller in scale, the scale that's defined as Kolmogorov scale is when viscosity and inertia are equally important. So Reynolds number based on that eddy is 1. So like initially it was thought, okay, like when viscosity is taking over, everything smaller is going to get killed by viscosity because it dissipates very quickly. But that's not the case. You have to go much, much smaller. And as the Reynolds goes higher and higher, you have to go even smaller than Kolmogorov. So things get harder.
My next question is that when we try to connect what you have said with what happens in reality in cloud systems. So could you please comment that the processes like updraft or downdraft or strong convections or polar jets, they are the ones they will actually determine the fate of a cloud. So in your scheme of computations, how they have been envisioned or how they can be envisioned if one has to extend this knowledge to the field geoscience, how they will be getting this?
Yeah, so that is the first level of decoupling that I told you. Like when I look at something far bigger than a meter, and then I'm decoupling everything that happens in a meter to that. All these convections, all the things, these big processes are happening on large scale, and I've pretended they don't exist, which is not correct. Which is not at all correct, but we can bring it in trivial ways. For example, I could have my box moving upwards, and therefore the temperature going down at the rate of the upward convection. So I could do things like that, which are, hand waving or simple ways of bringing in the large scales.
So are there possibilities of, for example, I can visualize that there's a updraft and some box is going up, but then at some height it would, be interacting with the polar jet. So the direction of polar jet is different from the vertical.
Yes.
So that
Yes.
box would be going in some direction which you need to model in your scheme of computation. So
Absolutely, absolutely. So
or how
yeah,
to do that?
we are not yet there, but yeah, you'd have to do things like that.
Okay. One more thing which I could not imagine, because many of the things I'm just trying to imagine what you say. But this Bessette Bosonet's history course, what exactly, I mean, layman like me, how do I imagine what that force is?
Okay. So it's a very good question. It's not an easy question to answer, but I'll try. So here is a particle. Imagine that here is a particle, and at time equal to 0, it's placed in a fluid. And now what's happening is that, okay, let's do it even easier. Let's take a plate like this. Okay, now I impulsively start this plate. So at time equal to 0, I make it go from 0 to u. Then like you can actually solve this problem analytically. It's the standard impulsively started plate problem. I can solve it. I'll see a boundary layer growing on the plate where the velocity will be plate velocity at the plate and 0 far away. And this thickness over which the velocity is changing will keep growing. Then like imagine now instead of this plate a sphere, and you're doing this thing at every delta t. So you're impulsively starting, you're changing its velocity. In other words, this thing is accelerating relative to the flow. And if you put that thing and derive it, you'll get the Bassett term. So in other words, like it's not enough what my situation is right now, but where I've come through determines my boundary layer, and my boundary layer determines my drag.
Thank you.
So Varanshi.
Thank you, Dr. Rama, for the interesting talk. So actually, we are solving the Navier-Stokes equation to simulate dust vortices on Mars. And we have reached up to 10 meters on our HPC. But as you said, reaching 2 meters is a bit difficult. So what we did was that we sort of took a steady state dust level and we tried to simulate the continuity equation and the force equation. And it seems that we got a pretty good estimation of the physical distribution of the dust. And also, we could very well separate that and simulate the electric field and lightning from that. But now my question is that the thermodynamics on Mars is very important. So that is where I want a suggestion that because this dust will absorb this radiation and very fast the conditions are changing on Mars. So what is there some method, which we can, because solving Navier-Stokes, we are solving that. We do see dust vortices forming here and there. But to actually simulate the physical conditions is very difficult. So some kind of a method, where we can go about to take some approximate thermodynamic simulations which we have shown. If you could have any comment on that.
That part which might be
Okay, great. For the dust particle, like when there are other forces on it, apart from just the fluid force, you'd have to write, let's say, a Maxi-Reilly, including other forces, and you could do that. And because for a small dust particle, everything is linear. So you could actually just sum up the forces. And if you could solve for a few particles and get an idea about how these forces are behaving, then you could think of coarse graining and writing it for writing, let's say, a field equation for the particles. So that would be one approach,
So,
actually.
for example, we have been able to neglect the interparticle cohesive forces, and which the community feels is quite good enough. So that has been accepted. The other thing which I want to comment on is that we believe that Richardson number and Manikov length, they are very important. So there we are trying to characterize different regions on Mars in terms of their turbulence, and then try to see the relationship with the dust vortices.
Right. I didn't emphasize too much on that, but the Richardson number is very important for the asperitas formation as well. So yeah, on the large scale, it.
Any other question? Yes, one question there, Kumar. Yes. Yes.
Very sad quick question. What is basically whether these theories will how applicable on the cirrus clouds where there are mostly there is ice and high altitude clouds?
Yeah, so ice is supposed to be very different from these, like from some preliminary simulations, we are seeing that, everything including its terminal velocity and its growth is very different, but it's being studied, but less is known. We're trying to do some actual simulations of ice particles with, resolving around them. And by boundary integral method, we're trying to do that.
I have a question. I think now we'll go to the young scientist there first. Akanksha.
Yeah, hello, ma'am. Thank you very much for the informative talk.
Thank you.
I have one question with the experiment that you shown over there. So as I could see the disc, they were at some kind of angle. There was some orientation. So basically, if we talk about the spherical particle, there will be no orientation as you release the particle. But like, why did you keep the disk at some kind of orientation? Why not release it straight forward? Or this orientation is contributing to some something to.
We've released the disc straight. They're all perfectly vertical. We not put any orientation there. Oops.
Or
Why isn't it playing? The orientation is coming with time because the way they interact with each other. Yeah, so that is not something we put.
okay, so anything related to this vertical part also or horizontal? Matlab, I just wanted to know something like why the vertical orientation or something, the horizontal orientation. Is there a difference? Something
Yeah, there is a difference. Like based on the orientation we choose, the clumping will be different. But we just chose the simplest one in order to just understand the physics of it. That was the idea. But now that we have written the equations, we can solve them for any orientation.
Okay, so some practical application related to this, like because in clouds we have tried to show the spherical particles only, but when it comes to the disk, matlab any practical example.
So like ice crystals are one example, like the previous question, like very, very high up in the cloud, you're more likely to get ice than water because the temperature is minus 40 or something. So like initially they form as ice crystals, which are not spherical. There are many, many situations like where particles are not spherical. Even sediments in the river are not typically spherical. So in all of these examples, volcanic ash, you find non-spherical particles.
And the theory, I may be wrong in this question also, but the theory that you have mentioned about the stability analysis, is it something due to the related with the horizontal cloud cover or vertical height of the cloud cover? Is this factor going to contribute somewhere to the theory or something?
Okay, there are no wrong questions. There are only wrong answers. So yeah, we've pretended that the cloud has a initially flat bottom, and we've taken a certain thickness for it. If we took a thicker and thicker and thicker cloud, then this asperitas thing would last longer. That's all. But the basic mechanism will not be dependent on the depth of the cloud.
Okay. Yes, last. I can give the mic to the first.
Thank you, ma'am, for the talk. I want to ask you, how do you quantify the interaction between the particles? Like, what is the force that causes the cohesion interaction?
So this is the simplest force, the Stokes-Let, where like each particle is considered to give a point force on the other one. And this is solved exactly for Stokes flow up to this order in the expansion. So as you keep increasing the order, there's more and more terms, but this is not a correct one, but it's okay when D is much bigger than A. So this is the point force we give. And we've written a similar equation for the orientation, how the orientation goes, because you can think of an ellipsoid as, let's say, two spheres connected by a rod. So, I mean, I'm just trivializing it. We've done it more exactly, but then like each sphere will feel a different force on it and it will orient. So the reorientation is another equation which we've written down. Does that answer your question?
Okay, I'll invite more questions from back, one or two before we close. While you're thinking, maybe I'll ask one, in terms of the experiment that you have done. You said in your talk that you have given sinusoidal impulse. You tried hard to get a sinusoidal impulse to begin with. Or is it, did I hear correctly? Or you said sinusoidally they are falling down because they are there.
Okay, what we've done is the following. we have a comb-like structure in which we have gaps for discs. And we've not placed all of them at equal distance, as you can see. So the horizontal distance, we've, spaced it in such a way, and this is the horizontal perturbation shown. The UX is the location now. The horizontal perturbation is like that, and it's almost a sinusoid. Whatever best we can do with a discrete version of a sine wave.
How do you give sinusoidal impulse?
That's the thing we've given. They just placed in a sinusoid.
Okay.
And then we let them go very gently, like we don't, at time equal to 0, they have 0 velocity.
And also the interaction is a function of the distance that which.
The interaction is a function of the wavelength and of the distance.
And in all of these estimations, you have not considered any effect of winds and other dynamics. Because only the gravity is the only thing that you have included.
Yeah, gravity drag due to the flow. Right. And the history and each other, those are the things.
And one last question from my side is in terms of the, when you say the Reynolds number when it's large, you don't have to do the calculations for the smaller scale, isn't it? Because that doesn't, there's no relevance for doing the calculations at the smaller scale when Reynolds number is high.
Yeah, so when the Reynolds number is very, very, very high, you have to go to, let's say, 5 times or 10 times smaller than Kolmogorov length. And then below that length, you need not go for the flow itself, but the particle needs to know where to go. Particles are way, way, way smaller than that. So for the particle is in Stokes flow, that is its Reynolds 0 relative to the fluid. So that we have to solve separately.
Thank you. Yes, I think one last question there. I think Akash. Wait, just wait for it.
Thank you for the wonderful talk. Just a simple question. In this, if you change the geometry of the bounding box, would you expect any sort of difference in the algebraic growth?
Yeah, if you change the geometry of the box, you will expect some change. It's going to be at higher order in this Stokes thing. So like, where's that equation? Yeah, this equation, see what happens is that every particle forces every other particle. But if I have a box which is, this wide, it's going to screen interactions bigger than that length scale. So every other particle won't, I can go with some nearest neighbors and get a reasonable theory. But if I make that thicker and thicker, that's just one example of changing the geometry. I'll have to add more terms in the series in order to get the correct answer. But the correct answer will be qualitatively the same. Maybe like in detail, it will be different.
If I might just add one more question. In the simulations, did you also consider the Reynolds number for the particle to be 0?
Yes.
But including the consequence of Stokelets, those simplified.
Yes. So here we just included the Stokelet. We even ignored the Bassett history.
Thank you. Yes, I think I'm sure there will be more questions, but I think in the interest of time, we should stop. And I hope that you all agree with me that this has been a wonderful talk by Dr. Rama Govindarajan, wonderful interaction. And so with this, I think she'll be here, so if you have any questions, you can just, she'll be in room 463. So maybe after lunch, 2:30 or so, you can interact with her. Up to 4:30. Yes. Yes. Thank you. And now I'll hand over to Yogi.
Thank you very much, Professor Rama Govindarajan, for an interesting talk. And also, thank you very much, Professor Pallam Raju, for conducting this session. Now, I would like to request our director, Professor Bharadwaj, to please hand over the memento as a token of appreciation to Professor Govindarajan. Thank you. And finally, I would like to invite Professor Vijay Kumar Sahu on stage for thank you remarks and formally closing this event.
Thank you, Bibha. Respected Rector, Dean, Registrar, PRF, my dear friends, colleagues, students, PDS, a very good afternoon. So we started in the mornings before noon, and now it has become afternoon. So I'm Vijay Sahu from PRL. So it gives me immense pleasure to deliver the vote of thanks for this event of third Dr. Bibha Chowdhury Memorial Lecture to everyone assembled here, as well as those participated, online. At the outset, I would like to thank Professor Rama Govindarajan for kindly accepting our invitation from PRL and gracing the occasion by delivering the talk in person. She honored the event with a wonderful talk on dynamics of small particles in flow, which was very informative, and there were many curious questions. The previous two lectures were given online, as Professor Goswami mentioned in the beginning, and this was the first offline talk on Dr. Bibha Chowdhury Memorial talk conducted by PRL. I also take this opportunity to offer my gratitude to our beloved director, Professor Anil Bharadwaj, for providing us constant support, guidance to organize this event and making sure that it is conducted smoothly and successfully. I would like to thank now the committee members of this event, Professor D. Palam Raju, the Dean of PRL, Professor Subhavati Goswami, and Dr. Bhusit Vaisham for shortlisting the speaker as well as organizing the event. Especially to Professor Goswami, who personally took the initiative to contact Professor Govindarajan and ensure that she visits PRL. We are grateful to the CNIT team, auditorium staff, and Dean Office for making necessary arrangements and live streaming of the talk. Thanks are also due to the Director's Office, Dean's Office, Registrar and Registrar's Office, Administration, Accounts, Transport Section, as well as Secretary of Theory Division for their generous help and support for conducting this event. In the end, I would like to thank one and all present here, as well as those joined us online, without whom this event could not have been successful. With this, I would like to thank all of you. See you again next year. Bye.